covering curved beams. And the first approach I'll be teaching curved beams is using Airy stress function again. And to back up a little bit, this is yet another application of Airy stress function. And the idea here is that with Airy stress function, you satisfy the equilibrium equations exactly, and you satisfy the compatibility equations exactly. And what you're doing here is you're coming up with a stress function that's able to satisfy the boundary conditions. And by imposing those boundary conditions, you're able to solve for the coefficients that are unknown in the problem. And that way you're able to solve the problem of elasticity in a convenient way. So that's what Airy stress function, that's how we used it. I apologize for that. And so again, to remind you, there's these equations, the governing equations of elasticity. We have the 6 strain deflection relationships. We have the 6 stress strain relationships, which gives us 15 equations and 15 unknowns. And that's very hard to solve by hand, as you experienced already, right? It's not easy to solve by hand. What will be more practical is to use maybe a finite element code that can do things for you. But yet you want to still interpret the results, make sure that you understand them, or hand calculations that are able to solve very specific problems where finite elements may not be very helpful because maybe the scale of what you have there in the finite element models is too large, and so you cannot model every feature in the structure. For example, an aircraft could have small rivet holes, and you don't want to model every little rivet hole in the finite element model because that will be computationally expensive. But yet you can maybe come up with the far field stresses and use the far field stresses to enable you to use hand calculations to then estimate the stresses near the rivet hole. So that's where the practicality can come into play. A lot of the concepts I'm teaching here that they are using in industry, finite elements is not the only way to go about it. We also talked about how the external loads is connected to the internal loads. The internal loads are the stresses that develop inside the body of material, and I can use those stresses to predict the strength of the failure or the limits of the design, and I can use that to then even calculate strains. And if I know the strains, I can calculate deflections. They're all connected in this, and this came from a book, which you can look at that chapter and kind of study that again if it's not clear. So the curved beam application I have today, the one I'm going to discuss specifically today, is very helpful for hooks analysis, chain links, punch press frames, automotive applications, also aerospace applications. Anytime you have something that can be modeled as a curved beam. In reality, the way I view this lecture is another lecture that gives you a perspective on how area stress function can be used successfully to model certain problems. So here what I have is and I'm going to go through a lot of equations. Just like in previous lectures, what I want you to understand is the conceptual parts and understand how that can be applied for the problem of interest. In this particular example, what you see is a curved beam with inner radius A, outer radius B, and it has moments applied at the end. And so the question that we have to really assess the structure that you're looking at here is, what are the stresses they're distributed in this curved beam when I apply those moments? And how do we tackle that problem? So we could use the Airy stress function approach, which satisfies the equilibrium equations exactly, the compatibility equations exactly. But then the question becomes, what are the boundary conditions for the problem? So anytime you're working with Airy stress function, you want to fully understand what are the boundary conditions of the problem. And looking at this diagram, there's a lot of things going on here, but let's relax for a little bit and try to understand it. So here, in this case, you have a curved beam, fairly thin in this case, and you have this cross section here. The height is h, meaning this distance from this point to this point is h. The thickness is t, and you can see here that's a centroidal, that's a centroid, or that's the centroidal axis, where this dashed line is shown. when I apply this bending moment, what's going to happen, think about it. If I were to take a piece of metal that's curved and I apply a bending moment in the way it's shown here, you will see that there'll be tensile stresses forming in the top, and that's in the hoop direction, right? Think about it. So if the center point is O and the curve being follow that center point O, then sigma theta theta, that's a hoop direction. That's a hoop stress direction. And that's the direction where tensile stresses are being developed. The variable R is being used here as a variable. So it can go anywhere between A and B. A is the inner radius and B is the outer radius. So what are the boundary conditions? And it's going to get a little bit busy here, but trust me, I think we can follow it. So let's look at, I'm going to just do one example on one surface, and then you guys can figure out the other surfaces. So let's look at the surface at R equals B. So R equals B, that surface is this one here. That one there. That's the one I'm talking about. That's the surface we're talking about. So if I were to look at what's going on that surface, we have a radial stress there, potentially, sigma RR. And then you have a tangential shear stress, sigma R theta. But on that surface, am I applying any tractions? No tractions, right? I'm applying no amount of tractions there. So therefore, using Cauchy's relationship, you can see that this must be zero because I'm not applying any radial traction, no traction is normal to that surface, and I'm not applying any shear traction to that surface. So that makes these ones zero. Do you guys follow that? Is that clear to you? And if you're confused, all you can do then, is always to slow down, spend some time understanding the problem. What I can do is draw a square. So I'll take a square out of here and draw it. You can see here that that's a radial direction and that's a theta direction, correct? So you can see here that normal to the surface is sigma RR and tangential to the surface is sigma R theta, because sigma R theta is the first index corresponds to the surface we're talking about, which is R, and theta here is the direction that we're applying the load. Okay, so hopefully that's clear to you. So looking at this, then you can see that that's why these stresses are zero. I can repeat the same process for R equals A. So that's at R equals A, and our R equals A, you have the same situation that at this surface right here, at that surface right there, you don't have any radial stress at that surface because there's no traction applied on that surface. In addition to that, there's no shear stress applied. Now, in the exam, maybe for the final, I could change it and I can make it so there's a pressure applied, right? How will you go about a pressure applied to this body of material? The way I will go about it. Who said that? And you said that? You said that. Excellent. Excellent. You're right. Superposition can be used. Okay, so given that we got the boundary conditions taken care of. If you had a situation where you're looking at the solution for a problem of a curved beam under bending load and pressure loads applied on the top surface, what you will do then is use superposition, because you know the solution for a problem of a ring under pressure. We know the answer to that. So now make sure that's clear to you. And I think we got that right. So now let's examine the next boundary conditions. They're a little bit harder to understand, but I don't think they're that hard to understand. So let's examine the first one, which is if you look at the end, at this end right here, let me highlight it for you. So looking at this end right here and looking at this end right there, there's no hoop stress, the hoop force, no hoop force is applied. So in reality, and you can put a T here, T is the thickness, and dr is a radial element. When you integrate over that surface, you're getting that whole area there. So in reality, what's going on is I don't have any axial force applied on this surface. And when I say axial, what I mean, let me draw it for you so you can see it. I don't have a load applied that way. Agreed? You see that? There's no radial force applied, axial force applied. So if I look at that direction, isn't that direction sigma theta theta? So what is the resultant force? Is sigma theta theta from the inner radius A to the outer radius B, correct? What is force? Sigma theta theta times dA, the area dA. What is dA? Is going to be an element, dr, and the thickness is T. So you get T times dr equals 0. But T is constant, so you don't have to write that there. You can cancel T. You know. So that's why you see that formula there. That's the boundary conditions on this surface and that surface. Any questions on this particular point? I'll let you think about that. So the first integral does not know whether it's in tension or compression, but we know there's no resultant force, and so therefore the resultant force is 0. So it does cancel out. You could have compression or tension. It doesn't matter. There's no axial force applied. What matters is the external force. There's no external force applied. So we should be okay there. What's your question there?
That's just saying that no matter like what radial line through the tube, there's no stress from the inner radius to outer radius along all the radial lines.
No, what this is saying, what this formula is saying is that there's no axial force applied to the surface. I'm not applying anything on that surface. Axial. I'm not applying that axial load.
And we're integrating it, and by going with that's just saying like going from like inner to outer radius.
So the question I believe is, if there's no axial force, how we're accounting for the variations of sigma RR, sigma theta theta from A to B? Not each of them, but the totality of that. It's not giving a resultant force that's in that direction, in this direction. So another way, an integral, I don't know if we know this, but the integral is also summation. You can look at a summation. You're summing small little pieces together, right? So the contributions, what is the area? D force equals the stress times the D area, right? The area is dr T times the thickness, right? So that's the area. So if I want to know the total force across that whole surface, I'll do an integral here, correct? But this force here is 0. I don't have any axial force. So therefore, what you see here is exactly what I have here.
Yeah.
Not in the axial direction. Yes, in the axial direction, but integrated through the thickness. Because this integral, limits of integral are r equals A to r equals B. So along the surface. Right now, there's no force. A resultant axial force. There's no resultant axial force. In fact, there is, because there's a moment applied. And to get that moment applied, the only way to do that is to do something like this on that surface. Apply stresses that way and stresses this way to get the moment going. But the resultant of it is not a value. So the question is, why there's no sigma theta theta on r equals B? Is that the question? Is that it? There's no sigma theta theta on this surface. On this surface right here, there's no sigma theta theta at the very top, on the top surface. Because when I draw a cube, let's draw a square, right? So I draw a square. That's representative of a square here, say, right? I look at this, that's r, that's theta, right? Let's draw what the stresses are for the square. is going to be sigma theta theta here, because theta is this, the first index tells you, or the first subscript tells you in what surface is acting on. Is acting on this theta surface, correct? And this theta tells you, the second subscript tells you which direction is going. That's this direction, correct? But this surface right here corresponds to the very top surface there. So looking at that one, that only has sigma RR, which is R phase, is on the R phase, acting on the R phase, and it's acting on the R direction. And finally, you have sigma R theta, which is pointed this way on that top surface, because it's acting on the R phase, the first subscript, and theta tells you in what direction it's going. And that's why you don't see a sigma theta here, because the first subscript tells you what surface you're putting that load. And you can see there's no, that's not the theta surface. This is a theta surface. Is that clear? Okay. So now looking at the moment is this one here. That's the moment. And you may ask me why that's the moment. Well, we can look at this surface here. Let's look at this surface here. And I draw that surface. Okay, that's the surface. Well, I draw it not quite right. Let's slant it the same way. So I'm drawing that line here, right? And what you have here is that there could be a sigma theta theta, right? So let's draw it, and then that's a centroidal point. So this is sigma theta theta, say. And what is the distance sigma theta theta to the neutral from this axis here, or from the point here O in the center, right? So if I want to take moments about O, you can see here that I have sigma theta theta times radius, right? That's your moment arm, radius R. And then you have thickness of the part. It should be dr, because I'm looking at increments of that dr. And then if I want to get the total moment, that's dm. If I want to understand what the total moment is, I integrate this from A to B, and that's what I get. So you can see here that I have all the boundary conditions defined now for this problem. I have the moment and the actual force defined. So the question becomes how you solve this problem. Well, somebody spent time figuring out what's the area stress function that best solves this problem. We already covered what the area stress function is for different problem, but for this problem, the area stress function is this one. And somebody worked it out and showed that the biharmonic equation is fully satisfied. If the biharmonic equation is fully satisfied, that means that the equilibrium equations and the strain displacement relationships and compatibility equations are fully satisfied. So that's the beautiful thing about Airy stress function, is that by selecting a function that satisfies the biharmonic equation, you essentially satisfy two of the major equations that we have, and there's less work to do. All you have to do now is to satisfy the boundary conditions. So with that said, are any questions on the go here into the recording? And let's make sure that's clear to you. Why is it negative? Great question. Sorry for not covering that clearly. So here, this surface is this. Well, let's make sure the pen works first, and then we can celebrate. That's the one that we're looking at, right? Correct. And then I'll draw that here. I'm drawing that line here, as you can see. Hopefully that's clear there. And then that's the centroid of that. And I want to take moments about here, right? So say I have this sigma theta theta, and that's a radius r, right? And I have to do incremental value of dr, right? So if you did the dr cross sigma theta theta, and then you went to Starbucks and you did it publicly, I think you will see that, well, people may think that you're out of your mind, but you could start doing hand signals. So the way I'll do it, I'll point my hand along R, and then I'll do cross against sigma theta theta. So that's making a moment that's negative, is going in the look at my thumb, is going into the page, which is negative. So that's why it's negative in this case. But I could have made it positive, is that when this person derived it, they derived it in this way. Okay, so yeah, so I think I just covered that last question on the moment part of it. The Airy stress function, I don't want to stress you out. No pun intended, we're talking about stresses here. But I'm not going to ask you to come up with Airy stress function. Because somebody probably spent months trying to figure out which one will make sense. You know, just looking at this, it's not obvious why this is the one. But it is possible to figure it out. It's not that hard either. And you can, but you should be able to show, that this equation here satisfies the barharmonic equation. You should be able to show that this satisfies the barharmonic equation. And you should be able to show, if I give you phi, you should be able to show that these are the stresses that correspond to this Airy stress function. And you know that because we learned that stresses are related to Airy stress function through these equations. We already covered that. So that relationship is established. You should be able to plug this in here to come up with a stress that's a function of Airy stress function. Okay. So given the Airy stress function, you should be able to calculate the stresses that go along with them. And you can see that they're given by these formulas. And then you can get this here. Now, the question becomes how I calculate these coefficients. How do I determine what these coefficients are? Anybody knows how we determine these coefficients? Now that I have this. Boundary conditions, who else said it correctly? It was only 3 people. You, one more person. I heard another voice. You, and you get 30 points extra credit, correct? So that is going to be the case. You have this stress that's a function of A1, A2, and A3, and I can find these coefficients. How? Thank you. Boundary conditions. Trick question. You thought I was going to say something else, but it is boundary conditions. So where are the boundary conditions? Have I discussed the boundary conditions yet? Thank you very much. 10 points for everybody that said yes. It is correct. Okay, just checking if you're awake. So here you can see here the tau r theta is 0. So apparently for this problem, for the boundary condition that we have, for the stress function that we have selected, there's no shear stress. And I think that makes a lot of sense. You can check it out later. But I'll impose this. I'll impose these 1, 2, 3, 4, 5, 6 boundary conditions into the stress functions, and then calculate A1, A2, A3, and plug them back into the equations here. So can you see that? We have 5 equations, and I should be able to solve for all these coefficients, right? If you wonder how, okay, let's do one just to see, okay? So sigma r at A is 0. So you put r equals A there, and now sigma r is 0 at r equals A. You know how to do it now? Okay, in the exam, am I going to ask you to get in this form, this beautiful form? Yes and no. What I'm asking you is, plug these numbers in here, each of the equations, show them what they look like. I'm not going to ask you to do it by hand. If you stay home, maybe yes. We'll have to see. But you can use Mathematica or MATLAB or a symbolic manipulator to let it do it for you. And if the variables don't make you happy because there's too many of them, in the exam, you assume, okay, assume A equals 2, assume B equals 3. Because what do I care about if the answer is perfectly right in terms of numbers? I care about the process. I want to know if you know what I'm talking about. Is that clear? Is that clear? That's what I'm looking for. We're not unreasonable here. If we're unreasonable in the grading, we have to talk about it. But that's not our intent. Okay. So far, those that felt that it was unreasonable, they end up realizing that they actually were wrong and there need to be some concepts to be learned. So, okay, so that's what I got for sigma r, sigma theta theta, and sigma r theta. Okay, you can see here the moment is provided here. A is the inner radius, B is the outer radius, R is the variable, the only variable in the whole thing. R goes from the inner surface to the outer surface. Is that clear so far? And N is this much right here. So N is in the denominator in here, and B and A are known. Do I know B and A for this problem? You know the inner radius and you know the outer radius. You plug that in and you get the sigma r and sigma theta. So now I can plot in Mathematica or some code, I can plot the radial stress and I can plot the hoop stress across the whole thing. Correct? I can do that. Given that equation here, given this equation here. So this is the area that we need to learn how to do. We need to know how to do this. I'm not going to make you come up with an Airy stress function. That's not a fair question. But what is a fair question is, that's the Airy stress function. Question number one, does it satisfy the biharmonic equation? Question number two, what are the stresses in terms of the Airy stress function? Question number three, what are the boundary conditions? I'm not going to tell you what the boundary conditions are. Question number four, what are the stresses? Use the boundary conditions to figure out what the stresses are. Are those steps clear? Okay, good.